Before I get to example 1, let's go through differentiation formulas. Some of these will happen today, specifically these first 3. The remainder will happen or actually this 4th one will happen also. Yeah, these first 4 rules are going to happen in the first 3 examples. The last 2 rules, product and quotient rule, are a little bit more involved, and they are in future lessons, either I think day 3 and 4 is when those happen. But first off, the first rule is simple. If you're taking the derivative of a constant, the answer is 0. So the derivative of 6 is 0. Derivative of 55, 0. Derivative of pi, 0. Any number, derivative 0. The derivative of x is 1. Okay, and if we just were to use the f of x plus h deal there, right? Limit as h approaches 0. F of x plus h, if the function's x, would be x plus h, right? Minus x, that's f of x all over h. Cancel, cancel, h over h equals 1. Right? So the derivative of x is just 1. Here's the rule that's going to be your best friend. It's called the power rule. And for me personally, if I'm doing any kind of function in calculus and I'm supposed to do a derivative, I'm going to ask myself before I do anything else, is there any way I can make this thing look like this? X to a power. If I can, the power rule states the derivative is simply the power multiplied by x to 1 lesser power. On top of that, if there's a constant in front of x, for example, let's say it's 8x to the 5th. All right, the power rule, if I'm trying to do the derivative of this, oh, and by the way, d over dx is a derivative operator. And let me just explain that real quick. If you see a plus sign, what do? A plus is an operator. It tells you when you see plus, you're supposed to add things, right? A minus sign means to subtract. A division sign means to divide. A d over dx means take the derivative of. It's an operator. So when you see d over dx in front of an expression, it says take the derivative of this expression. This is a power structure. That's what we're looking at. X to the nth power, x to the 5th power. Okay? The rule says that the derivative of x to the 5th power is n the power times x to 1 lesser power. If there's a number in front, you're going to multiply the power times the number in front. So 5 times 8 is 40, and then you reduce the power by 1. So 40x to the 4th is the first derivative of 8x to the 5th. Okay? No x plus h to the 5th power required. That's the power rule. That's the easiest differentiation rule in the books. So if at all possible, you can make your equation, your thing that you're trying to differentiate, into a power structure, x's raised to powers, then you can use that rule and it's worthwhile. All right. The last rule I'm going to talk about today is the sum or difference rule. If you're differentiating a sum or difference of functions, you can differentiate each function separately. What that means is if I have d over dx of 7x to the 3rd minus 4x squared plus 2x plus 73. Okay? Something plus or minus something. This minus this plus this plus this. You can add as many objects as you want, but you have this string of objects. Power function, power function, power function, constant. Okay? 7x cubed, the derivative is 21x squared. That's the derivative of that term. Negative 4x squared, the derivative is negative 8x. 2x, derivative of x is 1, right? So that'd be plus 2. And 73 is a constant, its derivative is 0. There's your answer. Alright? So basically you can apply this rule again and again and again for each term individually. Alright? So, going on to example 1, we got 5 problems here. They're all power functions. And the first one, x to the 6th power, find f prime of x. So this is the other way of asking you to find a derivative for right now. Find f prime of x. Okay, that's kind of what we've been seeing the last chapter. Okay, identify it for what it is. It's a power function. The power function rule says the first derivative of a power function is the power times x to 1 lesser power. So you subtract 1 from 6, makes 5. That is the first derivative of x to the 6th power. Look at part B. Y equals x to the 1000th power. Thank goodness there's a power rule, because x plus h to the 1000th power would be not very pleasant to do on our paper, go on the definition of derivative. This says find y prime, so y prime is going to be 1000 x to the 999th power. Okay, problem C. Y equals t to the fourth, find dy over dt. This is also means first derivative. The derivative of y with respect to t. Two guys invented calculus around the same time, discovered calculus around the same time. Isaac Newton in England and Gottfried Leibniz in Germany. Okay, Newton's calculus, he uses the primes, Newton did. And Leibniz used the dy over dt structure when he identified derivatives. Newton was using calculus to make physics easier, so if you're in physics and you've got an algebra-based physics, it's much more complicated actually than a calculus-based physics, because calculus and physics kind of go hand in hand. Not that calculus is easier than algebra, I'm not going to say that, but calculus-based physics is much more efficient than algebra-based physics. You got to go through a whole bunch of hoops doing algebra where calculus can break through a lot of things and do shortcuts. Leibniz was a philosopher, educator. He cared that other people understood calculus. Newton cared that he understood calculus. That's what he was about. He's a good guy, but he cared about himself and what he could use calculus for himself, where Leibniz was more, I want to know this, and I want other people to know this. All right? And they both wanted to share their discovery because they wanted to say, hey, look, I'm the smartest guy in the room, and I invented this. All right? And they borrowed stuff from other mathematicians throughout the years. But anyway, this is Leibniz notation. This is Newton notation. Take your pick. I'm good with both of them. But I do use both. So if I say find this, find that, know what they both do. But anyway, y equals t to the fourth, so dy over dt is going to be 4t to the third. Okay, problem D, we got the operator d over dr. Now, notice it's d over dr, before it was d over dx. Whatever this letter is, should match that letter. So, if it's d over dr of r cubed, it's the differential with respect to r. So, r cubed, r is the variable, we get 3r squared. Suppose, just for sake of argument, suppose it said d over dx of r cubed. What do we think the answer to that is? Again, this letter matches that letter, which means we have to differentiate using r as a variable. That. So d over dx of r cubed. Anybody want to venture a guess as to what that is?
Same thing.
Not the same thing.
Does not exist.
It's not, does not exist either.
0.
0 is the answer. If x is the variable, everything else is a constant. The derivative of a constant is 0. Okay? So if this letter does not match that letter, that's going to be a constant. It's going to act like a constant. Its derivative will be 0. All right? So just keep that in mind. I don't know if they're going to do that to you, but if they did, that's how you handle it. Finally, one more operator here. Big D sub u. That's the same as d over du. Okay, so big D sub u, find the derivative of the function with respect to u. And notice we have u to the mth power. So u is a variable, m is acting like a number would act. Okay? So the rule tells me if I have the letter raised to a power, I'm going to take the power, whatever it is, and take that times the letter to one lesser power. So mu to the m minus 1 will be the derivative of that. So in each case, make sure you make a distinction between what a variable is and what's acting as a constant. If something's acting as a numerical value, treat it like a numerical value will be treated. In this case, m is a numerical value. The numerical value gets multiplied by the letter to one lesser numerical value, so that's the best you can do in that expression.